his blood vessels to try to maintain homeostasis temperature of 37 degrees centigrade. Blood vessels will widen and travel closer to the skin, allowing cooling of the blood. Mo's blood will also be redistributed vascular shunt away from his organs such as his liver and kidneys to supply his working muscles with more oxygen. Breathing rate. An immediate effect of exercise is an increase in breathing rate to accommodate an increased demand for oxygen and an increase in CO2 that needs to be removed. The changes in levels stimulates the respiratory control center in the brain to increase the body's breathing rate. It sends an impulse to the intercostal nerves and muscles to increase the frequency of the contractions, increasing the rate of breathing, which increases the amount of oxygen supplied to the alveoli to diffuse into the bloodstream. This allows for gaseous exchange of carbon, which is also being produced at increased levels. After exercise begins, the receptors in the muscles and joints signal the extra demands to increase the breathing rate. An elite athlete at rest uses 250 milliliters of oxygen per minute, and at maximal exercise 3,600 milliliters per minute. After the body's initial response to increase the breathing rate, breathing rises at a slower rate and levels off in steady-state exercise until the exercise stops. Mo Farah's breathing rate will begin to increase even before starting due to the anticipatory rise. As he begins training, his breathing rate will increase. If exercise intensity is maximal, breathing rate increases until exertion. Tidal volume. Tidal volume is the amount of air breathed out per breath. It is approximately 500 milliliters per breath for adults at rest. Minute ventilation is the amount of air respired or expired in 1 minute. It can be calculated by the tidal volume times frequency of breaths in 1 minute. Tidal volume will increase with the amount of exercise taking in more oxygen to supply to the working muscles. During exercise, the tidal volume will increase up to 3 to 4 liters for athletes. As Mo Farah begins exercise, his body will require more oxygen for respiration in the working muscles and will need to remove more carbon dioxide, so the depth of his breathing will increase. The receptors in the working muscles and joints send a message through the nervous system to increase the minute ventilation. This causes tidal volume and breathing rate to increase. Elite athletes such as Mo Farah adapt by increasing the tidal volume rather than increasing the breathing rate. The deeper breathing can increase from 70% at rest to 85% of total ventilation during steady-state exercise. Once the athlete stops exercising, his tidal volume and minute ventilation returns to normal level. Oxygen dissociation curve. The oxygen dissociation curve is a curve that plots the proportion of hemoglobin in its saturated form on the vertical axis against the partial pressure of oxygen on the horizontal axis. It is an important tool for understanding how our blood carries the and releases oxygen. It relates oxygen saturation and partial pressure of the oxygen in the blood. Most oxygen is transported in the blood by hemoglobin. Oxygen reacts with hemoglobin to make oxyhemoglobin. The binding of oxygen and hemoglobin is dependent of the partial pressure of oxygen. Oxygen combines with hemoglobin in a high density of oxygen. For example, the lungs change in the blood. Changes in the blood, carbon dioxide levels and hydrogen ions concentration causes shifts in the oxygen dissociation curve. These shifts cause oxygen to be released in tissues and to increase oxygen uptake in the lungs. During exercise, the blood becomes more acidic because of the increased production of carbon dioxide. During steady-state exercise, increased temperatures and lower blood pH concentration affect the oxygen hemoglobin dissociation curve, so that more oxygen can be unloaded to supply the active muscles. Aerobic system. The aerobic system produces far more ATP than any other energy systems, but it produces the ATP much more slower, therefore it cannot fuel intense exercise that demands a fast production of ATP. This is ideal for steady state, low intensity exercise such as long distance running. Although it takes a couple of minutes to supply the energy, its main advantage is that it can supply unlimited energy as long as there is a store of carbohydrate, proteins, or fat stores, and the athlete remains hydrated. Energy system continuum. Most sports use continuation of the energy systems. ATP sports are used for 2 to 3 seconds. ATP system is used for the next 3 to 10 seconds. The lactic acid system is used for periods of 10 to 180 seconds, and thereafter the aerobic system is used. Muscle spindle. Muscle spindles are the proprioceptors located in the skeletal muscles. It detects the length and speed of the muscle change, and it helps the antagonistic pairs work together, as it measures contraction and relaxation. When muscles lengthen, the spindles are stretched, which achieves the muscle spindle that sends a message to the spinal cord. The spinal cord sends an impulse to the muscles via motor neurons, telling it to contract with greater force to slow the speed at which the muscle is being stretched. This is called the stretch reflex. The strength of the muscle's response is determined by the speed of the stretch. So if a muscle stretch is rapid, the response is a greater frequency of the motor neuron, and the more force in the muscle contraction, it has to happen quickly to prevent injury, so only travels to the spinal cord and is involuntary. It protects the muscle from stretching too much and preventing injury. With regular steady-state exercise, the body creates a smoother movement. Golgi tendon organ. Neuromuscular responses on muscle spindle and Golgi tendon organs provide sensory information about the intensity of the exercise. This allows coordinated movement patterns. The Golgi tendon organ is smaller than the muscle spindle. It is a sensory receptor organ found in the origins and the insertions of muscles. It detects tension which is applied to tendons. It moderates the contraction. In this way, it allows Mo Farah to train at steady-state exercise levels for long durations, as along with the muscle spindles, it moderates the muscle contractions, preventing over to be completed for the duration. Blood flow. Blood flow is controlled by pressure. This is achieved by pressure by the vasoconstriction and the vasodilation. Vasodilation is the widening of blood vessels due to the relaxation of the muscular vessel walls, particularly in the large and small arterioles and large veins. Vasodilation involves an increase in the diameter of the blood vessels, resulting in an increased blood flow to the muscle areas supplied by the vessels. Vasoconstriction is the narrowing of blood vessels resulting from contractions of the muscular wall of the vessels, particularly the large arteries, small arterioles and veins. Vasoconstriction involves a decrease in the diameter of blood vessel wall, resulting in the restriction of blood flow, stated by Mark Adam et al. 2010. The average cardiac output is around 5 liters per minute. When blood is circulated around the body, some organs receive more blood than others. However, during exercise, the working muscles need a higher amount of blood in order to supply them with oxygen. Energy. The body is able to redirect blood flow by constricting the blood vessels, leading to organs that do not require such a large blood flow and enlarging the blood vessels, feeding the muscles that do need it. This process of blood vessels contracting is called vasoconstriction, and the process of blood vessels dilating is called vasodilation. Thermoregulation. Increased plasma volume due to steady-state exercise supposed report sweat glands function during each stress and maintains the correct plasma volume for the demands of exercise. A trained athlete stores less heat early during steady-state exercise, reaching a thermal steady-state sooner and at a lower core temperature, and trained per Mark Adam et al. Stated. Thermoregulation is the process of maintaining a constant body temperature at about 37 degrees Celsius. When exercising at a steady state, the body begins to produce heat, and the body needs to lose this excess heat to maintain the homeostasis levels of 37 degrees. This is done by enlargement of blood vessels, vasodilation, and movement of blood vessels closer to the skin. Simultaneously, the body begins to sweat. As the sweat evaporates on the skin, it cools the skin surface. This cools the blood traveling close to the skin. These are the graphs showing the steady